Hello everybody. Just checking as usual at the beginning that you can hear me okay, microphone's working. I can see my little lights lighting up in my streaming thing, so it's highly likely that everything's okay right now. But I'll just make sure. I'll just check chat and make sure. See what our delay is today on responses. Good morning, Simply Me Joe. Yep, sounds like it's okay. And the one and only Southwester, is it? I don't know, SXSW is South by Southwest. Anyway, and hi Mike, how's it going? So, today we are in one of those parts of the course where we're in between things in a sense, you know. First assignment is nearly entirely wrapped up. Not many left to mark. I did send a notice out yesterday, just kind of pinging everyone about that, just to say, if you want to know how things went in the first assignment, there should be comments in the actual code itself, in the marked version of the submission, so you can check that out via the view marking and stuff like that in the course website, and then you'll be able to see what your tutor has been saying about where the points are readable or less readable about your assignment. There's also a little bit of auto marking in there as well, so we've got stuff like something similar to the 1511 style, which puts some comments in your code saying, okay, here are some things that might be an issue. And so a lot of that stuff will be handy if you want to sort of maximize the readability of your code for future assignments. If you do want more information about how your particular assignment went, I think one of the best times to do that, especially at the moment, because I think that now that they're not in person, people haven't been spending the full amount of time in the labs anymore, because maybe it's not the same without your tutor kind of walking around and helping you and stuff like that. So to get one-on-one time with your tutor, I think in a lab is actually a really good time to do that. So if you wanted to ask them to clarify feedback about the assignment, or even to ask them about, okay, I understand this is the mark I got, how do I get better next time, you know, how do I change my style for the better, you can actually talk to them about that in the labs, because there's a bit more time in the labs now that they're online, for people to actually get one-on-one help, which I think is pretty good. If you're having trouble or anything like that, your lab is now a place where instead of having to necessarily compete for your tutor's attention, it's actually easier to get your tutor's attention in the lab than it used to be. What was I gonna say? What else are we working on? At the moment, we're kind of deep into the idea of linked lists. Actually, I'll go into the lecture itself, because we're talking about the lecture. We're talking about some linked lists in the lecture. I actually have a lot of revision slides in this lecture. Whether I go through them all is another matter. I may go through them reasonably quickly. So, over here. Where were we at last week? So last week we finished a working implementation of linked lists. So we got our sort of battle royale example, and in that oh, hang on a second. While I'm here, there we go. Yeah. It doesn't quite work because I don't want to cover up the text, but hang on. If I look this way and I go, did that work? The arm nearly matches up. Anyway, always got to get involved in the memes. So, the Battle Royale example had some crucial elements in it that will allow you to learn about how to work with linked lists. So one of them was insertion into linked lists, the other was removal into linked lists. The previous week we'd also looked at how to loop through linked lists, and we also want to just kind of keep in mind how we're working with things like memory allocation as well. So we put a lot of that stuff in the tutorials and labs this week. So they're a bit different this week because we missed out on Monday. So the first tutorials are actually after the first lecture this week, and that's usually not necessarily the case. Usually a lot of people are doing the tutorials before the lecture. This week's the first, or the only time this term that's going to happen, just because of the public holidays. So anyone who missed out on a tutorial lab yesterday because yours was scheduled yesterday, you can check out the class timetable, find out when another tutorial lab session is running, and just go along to that one. I wouldn't suggest ever skipping on the tutorials and labs. I think that the majority of the learning in the course is actually done in the tutorials and labs. I might like to think as the lecturer that my lectures are important, but I know that for a lot of people, trying and doing things yourself, so getting the chance to make the mistakes for yourself is potentially more valuable than just listening to me talk about things. I know it all has to be pieced together. I know that you need the theory from me first before you can go make your attempts and then see whether things work or not. But I find that a lot of the times, if we're going to count exactly when things click, when people really get stuff, it's usually in a lab. So it's usually in the situation where you're trying to do something, you ping the tutor and you go, why is this working or not working, and you have a chat about it, and then you get some good results out of that. So we've got insertion and removal of nodes, and we have the ability to remember how we allocate and clean our memory, because we actually had a loop through where we were cleaning all the memory in the linked lists as well. So what are we covering today? We're covering a new topic called abstract data types, and this is a funny one, right? Because I think you may have noticed this, is that there are never really any new topics in anything I teach you in COMP1511, because hang on, put myself back out of the way now. Let me just check a couple of other things. Electronic buzzing sound. I'm not sure exactly what that is. I'm going to assume it was the fan on my computer again. Jeremy's asking you about how to get the feedback for assignment 1. Yes, and Michael there is answering that, so that should be okay. Good morning, Tom. How's things going? Okay, so what we're covering today is abstract data types. And it's a funny thing, because like with a lot of other things that we've covered in the course, that I'm not really covering it for the first time when I introduce the concept to you. This one in particular, we've been going over this for quite some time. I've actually dropped hints about this particular topic at least in 2 or 3 lectures previous to this. So what this is, if we go back over the multi-file projects, when I was first telling you about how we can put multiple files together, how we can compile them and things like that, that there's something called a Typedef that allowed us to make one type look like another type. There was ways that we could present certain functionality in an H file, and also hide certain functionality by pushing something into a C file that another file wasn't able to see. So all of that stuff that I was presenting to you builds together into this idea of what's called an abstract data type. And the abstract data type is the ability for us to say to someone, here's a thing, you can use the thing, you don't know what it is, you don't know how it works underneath, but you're allowed to use it as an abstract idea, and you'll be able to work with it. We'll go into a bit more detail about this in a second. So, quick recap. I'm going to do this pretty quickly, because I put a lot of slides in here about linked list recap, but I'm going to not skim over these at least a bit quickly, and we'll get into the new topics. But I thought that linked lists being such a big topic that I should at least come back through these. So, structures for linked lists. Each element of the linked list is a structure in and of itself. That being the case, they will all be identical structures, maybe with different values in them, but identical structures. Each one always has a pointer to another node of the same type as itself. So linked lists will go from one node to the next in this chain, like it is here with these next pointers. Each node in the list is also going to carry some information, which is the data here. If we want to try, this is just going back over the things that I haven't got the looping in here, this is just insertion and removal that we worked on last week. If I want to add a node somewhere in a linked list, and this means I could add the node at the beginning of the list, at the end of the list, or somewhere in between. The most I guess, difficult to work with, most interesting case is adding in between two other nodes. So if I was to create a new node like this, I would create a new node in memory by memory allocating that node. And so there's a lot of functions we could call, like I could make a create node function that has malloc in it, and malloc would create enough memory for one node, like so. This doesn't make it part of the list yet, it just makes it a node that's sort of floating in memory somewhere. To connect it up to the list, what I need to do is attach it to the rest of the list first by copying this first node's next pointer, and then to make sure that the list from the beginning reaches this node, I would then move the first node's next pointer to aim at this new node, and then this thing's all chained up together like a nice fully connected linked list. Head points at the first one, they all point one after the other at the next one until the final one says, alright, we're done here. I've now pointed at null, I'm the last element of the list. Someone's asking you about, James is asking you about help sessions. I think Michael's giving you an answer there. Yeah, cool. That should be fine. Okay, so that's insertion into the nodes, into a linked list, and removal from a linked list is a little bit simpler than insertion, because we don't have to change as much stuff, but it's good to know at least how this works. So we find the node we want to remove. So example here is we want to remove the second node from this list. The first thing we need to do is kind of, in a sense, rebuild the list around the gap that the second node is about to leave. And we do that by having the first node bypass the second node, by having its next pointer skip the second node, by going to the second node's next. Instead of pointing the second node, we take the second node's next pointer and we go, okay, we're going to go there, which skips the second node out. This means that at this point, the first and the third node, and whatever potential nodes, it might be a fourth, fifth, sixth node, whatever, are in a valid linked list again. Because there's a pointer aiming at the first node points at the third node points at null. They're all in a chain of a linked list. The other thing we need to do now, though, is to get rid of the node we've just removed. So we had this second node, and we removed it. We're going to free it from memory, like so, which means that while we're working on these things, we do want to have pointers keeping track of which nodes we're working on. Because if at this point we bypass the second node without retaining a pointer to where the second node is, we're going to lose it. And if we lose it, we can't free it, right? So if we don't have a pointer somewhere pointing at this second node, then it's going to be gone forever. So we have our first node bypassing our third node. Second node we keep track of using a pointer to know where it is. Using that pointer, then we can free that second node. You want to look at the code of for these things, check out the code from last week. If you're unsure about any of this stuff, last week's 2 lectures are definitely worth going back over, because we've got a whole lot of detail there, and I work the whole thing from scratch. So not only do I explain these particular slides in more detail, we also go through and translate all of these concepts into code. It's interesting because a lot of this stuff about like insertion and removal of nodes is a deceptively small amount of code. It's interesting to see how little code you write in order to get these things done. But I think what's more important than the lines of code itself is understanding the concepts and then trying to translate those concepts into code. I would say that memorizing code in this case is not as useful. I mean, sure, it works, but it's not as useful as making sure you have the understanding of how these nodes actually fit together. When I'm working with linked lists and when I'm working with structures like that, any kind of structures with pointers to other structures, I will nearly always draw pictures when I'm thinking about things. So usually when I'm planning how to write a program, I'll write notes. So maybe I'll write notes in a Google Doc if I know I need to share it with other people. If I'm writing notes only for me, I might do them on paper. But when I'm working with linked lists and things, those are nearly always diagrams. So you've seen all the Microsoft Paint stuff I've been doing. Boxes and arrows, right? I think it's useful to get familiar with that if you want to work a fair bit with linked lists. And you are going to need to work with structures like this a fair bit, because the idea of a structure that references another structure is very common. in computer science, and they get much more complicated as well. So I don't know if anyone's ever seen like a data flow diagram where you can be like ask questions about which character you are in your favorite TV series, and it's got this kind of things, and you get to the end, you go, "You're Captain America." It's like, haha, he's an idiot. Anyway, but you know, so you have like chunks of information with arrows pointing at other things, different arrows that could go off in different directions. A lot of that stuff turns into like decision-making things. If we wanted to, we could draw diagrams of every single program that you've ever written that says there's an if statement, and the if statement branches it into two different possibilities. There's a while loop. The while loop means there's an arrow that goes back to something else. So you could have a few boxes and an arrow that goes back to the top, and the arrow might have an if statement in it saying, okay, we might go back to the top, or we might go on to something else, you know. So if we wanted to, we could show the flow of what we're doing with all these boxes and arrows and stuff like that. When we're doing with linked lists, the boxes and arrows refer to pieces of memory and information that goes in between them. A lot of questions there. A lot of questions happening. I think Michael's answering some of them. Paris, you haven't watched the last two lectures. Will I understand the content in this one? You will understand some of the content in this one. When I go into the details of the implementation, it might be fiddly, but the idea of the abstract data type, you probably don't even need the last week of lectures, because this is going to look at things like files, C&H files and their access, so it's probably still going to be worth it. But if you want to, you could go and watch them and then watch this one afterwards, or you could watch them after this and see how it goes. It's kind of like watching a TV series out of order. Not all of the episodes are exactly sequential. There is a little bit in this. So you might not be on the main story arc right now. There was a whole lot of drama last week where we found out that someone was alive even though we thought they were dead, and then they came back, and no, none of that happened, but yeah. Yeah. George is asking, how would you be able to access nodes further down the list? Do you have to loop through, or could you do a first, next? Both of those will work, George. If we loop through the list, yes, definitely, we can get further into the list. If we go first, next, we can get deeper into a list. Super dangerous, however, if I write first, next in my code, and I have a list that only has one object in it, then that first, next is me asking for what is the next of a null pointer, and since the next of a null pointer doesn't exist, my program will crash. So be careful about explicit nexting. Looping through and checking that there is a next every time you loop through is a little bit safer. I think Michael's probably answering those. Michael and Tom are answering those. I should probably not necessarily take part in everything that's happening in the chat, because we've got tutors in here answering the questions already. Paris, up to you. You can leave and go in order, but if you want to hang out with everyone, you can hang out. Like, it's up to you, because like it sort of depends whether you want to watch this as it happens or watch it later on video. It's probably not that much different, really. I mean, like, what you're viewing is going to be the same. It's only if you wanted to ask questions in real time that I would suggest stick around for this one and then watch the others later. Up to you. There's talk of Dragon Balls and Tom being removed from the Battle Royale multiple times and things. Yes. Okay. So I love that COMP1511 has a story arc and stuff, and it's obviously me always beating up on Tom and him having to do all the work for the course. So this is something that you'll find over time, is that the lecturer is sworn in and we do our talky thing, and we get to be the head of the course and all this kind of stuff, but really it's the subject admins are doing all the work. You know, they're the ones like updating all the course content and stuff like that, making sure it works and things like that, and us lecturers are just like, oh, you know, whatever. Except for this week. This week I put together the lectures and the tutorials and labs for this week, but most of it was stuff that I'd used previously, and I was just piecing together things, so it wasn't even that hard. Anyway, let's continue my recap. We were talking about linked lists, and I want to talk about multi-file projects again. So these are a couple of things that I think that are worth remembering before we go into abstract data types. So separating our code into multiple files, we go from having just .c files. So .c files are pretty easy to understand because that's everything we've worked in so far. But now we've got .h files as well. .h files still contain code. It's not different to a C file in terms of the syntax and everything that's in it, but it's different to the C file in terms of its purpose. So the .h file only has the declaration of functions. They're only the prototypes. So there's no curly brackets or code in them. They just say, this is what the inputs and outputs of this function will be. I don't know what it does. You'll figure it out. But it has comments in there that says, okay, this is what this function is intended for. But you have to go look in the C file if you want to know exactly how it does what it does. So the .c file is the implementation file, and that has all the code that runs. So that has all the line by line. It does this, then it does this, and then it does a while loop. It goes through these things, these ifs and elses, and all that kind of stuff that is not in the header file. We have other files as well, and those files can include the header files in order to get access to the functions that the header says it has. It's important we remember that we're only ever going to include header files, and we're only ever going to compile C files. I think I've actually got that on a later slide. It's always the way. I always talk about the later slides by accident. Okay, so the reason why we do these things, the reason why we separate things into files, there's a couple of good reasons why we do this. Sometimes we're going to build up a library. So a library is like a toolbox. It has certain capabilities that can do certain things, which means we might want to have something that we've created and include it multiple times in multiple programs. So for example, standard input output.h. That is a library. It's one of the C standard libraries. It is a .h file. It is a header file. So just the same way that we're creating our own header files. What are we looking at? 700 students times by, I would say, about 50 programs per student. So we've included that file, I don't know, we're getting on like sort of 3,000-4,000 times. We've included that file as a class so far this term. So if we have reused that one file nearly 4,000 times, because every program that we've used has used standard input output. We've been printing stuff to terminal to see what's happening in our program. So that's a really good example of why we would separate something into separate files. Otherwise, we would have you rewriting something like printf and scanf in every single program that you're doing, and that would be just this huge waste of repetitive writing of code, as opposed to you getting repetition a different way, which is practice on things which are actually the concepts that we're teaching. So the library is there to be reused because the capabilities it gives us are available, we want to have available in every program. Depending on what's in your libraries, you may include them in multiple projects and things like that, depending on the situation. Here in 1511, less so, because everything we're doing is very kind of structured to teach you specific things at a specific time. But later on, people tend to carry around a toolbox with them of H files and C files, where they can say, oh, I did a thing that was like a complete linked list thing that could do insertion, removal, linked lists, and stuff like that. And so if I included that header file in any other project, then that would do all my linked list implementation for me. I never have to rewrite them. So people do that. People carry around libraries that they reuse for stuff, and that's kind of handy. A lot of experienced C and C++ programmers have like a little folder full of those libraries, and they go, oh, I can pull this in for this project. Especially if people work in the same industry for a long time, they will have their little packages that they reuse. So that's one reason why we might do it. The other thing that makes it really good is I can have some information in another file, and that information I can say it needs to be used in a specific way. If you don't use it in the right way, you can change things by accident. You can screw it up. You can put my ordered list out of order by accident if I gave you actual access to it. And so instead of giving full access to a struct, for example, what we give is only access to functions. And these functions might say, oh, you can add something to this struct, you can remove something from this, you can You can check what's in it, you can list certain things, but those are the only things you can do. You cannot go into the struct itself and say, okay, what's the data inside? I can now edit the data inside. So what you're doing is you're protecting it from being edited the wrong way. Going on to the use of these, I think I already said this already. The implementation files will be compiled, the header files are never compiled, they'll be included. Likewise, when you want to link these files together into their projects, any file that includes the header file will have access to all the functions that are in it. And you will never include a C file. Including a C file is dangerous because that breaches that kind of boundary that I had before, saying, no, you can't access the stuff that's in the code because you shouldn't have access to it yet. So the implementation files are never included. The header files are included. The header files are never compiled, but the implementation files are compiled. The other thing is, if you have a C file that matches an H file, we usually know this because we name them the same, they go together in pairs. Is that if you have the C file matching the H file, it has to know what's in the H file. So it has to say, okay, these are the functions I'm supposed to implement. So I'm supposed to make sure that all of these functions work. So my C file will have to know what those functions were. So the C file will include the header file. Good example for this, for everyone who's already working on assignment 2, is how beats by CSE is set up. So it has a beats.h and a beats.c. And the beats.h and beats.c are a perfect example of what we would call an abstract data type. So the abstract data type is, here is a beat. You don't know, if you include beats.h, you don't know how beats.c is implemented. So you don't know exactly what the code is that makes a beat a beat. You don't know, if you're in the main file, if I'm in the main file, I'm looking from that perspective, I've included beats.h. I've been given certain capabilities. So it says, these are the things you can do with a beat. I don't know that it's a linked list. So I have nothing in the main file that says beats and the idea of a beat has a linked list underlying it and this is what it does. What I know is a beat has notes in it. It can have a certain number of notes. It can have 0 notes or it can have many notes. I have ways of creating them. I have ways of counting how many notes are in it. Actually, it's counting notes within octaves in it, you know, that kind of thing. And so I have capabilities that I can use, but I don't know how it's built, and I don't need to know how it's built to be able to use it. So all I have is the functions, and I can say, okay, I'm going to call those functions, and I'm going to say, these are the things that that I would like to do with a beat. And then if I try to do something that a beat is not capable of doing, those functions will be able to stop me from doing that. So if I call a function to add a beat that's the wrong type, add a note that's the wrong type to a beat, so the octave's incorrect or it's not in ascending order or something like that, then the function will be able to tell me, no, that was incorrect. As opposed to me getting access to the actual linked list and just adding stuff to it and then causing problems. So that's the way that beats.h and beats.c are kind of different in how they work. So my main will include beats.h and it will use those functions, but it will not include beats.c and it won't have any access to it. The other files are the test files as well. Test beats.c at least does also include beats.h, and then it has a few things that it's going to use. So you can see in this case already that we have 2 different projects, each with a different main. So test beats.c and main.c are different files with different main functions, but they both include beats.h. So we're already seeing how we can create 2 completely different programs using the library that we've created, which is the beats library in a sense, where the beats library gives us the access to the capability to do things. I probably shouldn't necessarily call it a library. It's not necessarily a library, but I was going to say the abstract data type of beats, which says, here is the idea that a beat has certain notes in it. You can use the idea that a beat has certain notes in it in many different possible programs. So I could use it in a music composition program. I could use it in a program that's there to convert this programmatically created thing into musical audio. One of those exists. Actually, Tom's already been working on the synthesizer that people can do. Tom is 4,000. It is 4,000-ish, isn't it? 5 times 700 is 3,500, whereas I said 3,000 to 4,000. So I was allowing the fact that not everyone has done exactly specific number of exercises. Anyway, couple of questions there. Oh, I'm going to let. Yeah, I'm gonna let people like the tutors answer those questions. Tom, did I mean to release the Week 9 Student Lab? Yes, I did. Did I not? I think I wrote it all, and then I didn't actually set the timing for it to be released. So that's annoying because that's been ready to go for ages. Yeah, Tom, I don't know if I've actually. I don't want to look at it now because like already in the lecture, but I think I haven't released tutorial in lecture 9, have I? Because I'm realizing now in the back of my head that I didn't set the release time on them. Could you set them to release now, unless I have already? But I have a feeling that I didn't. And I apologize to anyone who wanted to start working on them over the weekend. They were ready to release yesterday, and I forgot to release them, I think. Yeah. Thanks, Tom. I mean, we've got an hour and a half until we need them to be released. Anyway, okay. So looking at this idea, we have a good example that everyone's sort of already been looking at to a certain extent for the for an abstract data type, which is a beat. And we know that the abstract data type has an implementation underneath, that it has linked lists in it, but we know from the perspective of the main.c and the testbeats.c, the files that are including beats.h, they don't know that there's a linked list underneath this. All they know is what capabilities they have available to them. They know the functions that are available, and they know they can call those functions, and they know that there's a thing called a beat. If they look closely in the type definition in beats.h, they'll see that the beat is actually a pointer to a struct called a beat, but they will never know what that struct is. All they know that it's a memory address, and they can use that pointer. And so they will refer to it as a beat, the capital B beat. And that's here in this Typedef. Actually, I'm going to talk about Typedef in a second. Let's introduce what this stuff means for abstract data types. So abstract data types are like types. So types like integer, like double, like struct node, like char, like integer pointer, all of those are types of variables. An abstract data type is the ability for us to create another type, and these are much more complicated types. We're just building up into a more interesting level of what we can do with things. So we can give things a name, in for example, a beat. We've given it a name, and we can say these are the ways you can interact with this type. And so we give it a set of functions that say, okay, you can add notes to this beat, or you can create the beat, or you can free a beat, that kind of thing. So simple things like that. These are the only things you can do with a beat, and you will know what you can do with a beat because in the header file you will have the functions that say these are the exact things you can do. The beat.h hides what's in the beat.c. So the beats.c, sorry. In beats.c, you have all the information, you have all of the sort of open raw data that makes this stuff work, all the programmatical content that actually makes the beat work, but you can't access that from the beats.h. So when you are including just the beats.h, you can only use the functions that are in it, and then they will then do what you need them to do, but you don't know how they work. You just accept that they do. One of the ways that I like to explain this situation is I'd usually do this with like a hands up or something like that, but I'm going to assume that a significant percentage of people who are in the lecture have driven a car, or they've seen a car being driven, they've been in a car, like it's just a pretty standard thing. We know how a car works in that we know that when we turn the steering wheel either way, the car goes one direction or the other. We know when we press the accelerator pedal, the car goes forward. When we press the brake pedal, the car tends to stop. We know there's a gear stick that does these other things, all right? We can see the functions of the car. Those are the functions. If I call those functions, the car goes certain ways. If I had access to the engine of the car, I could then have this idea that you can put a certain amount of fuel into the engine when it's running, and it makes the engine spin faster. So the more fuel I put into the engine, the faster it spins, the faster the car goes. The engine's power goes to the wheels via a transmission, which is all this other stuff. To be honest, I don't know how most of that stuff works. Yet, I have a driver's license and I can get around in a car. I can go hundreds of kilometers in a car, totally fine, without ever having a full understanding of how the internal combustion engine works, or why it works, or what it does. So, in a sense, the underlying functions of the car are abstracted away from me. I don't understand them that well. But what I do understand is if I push the pedal, it goes forward, and I push the other pedal, it stops moving. So I don't know how braking systems work. I don't know how suspension works. I mean, I've got a vague idea. I do work on the SunSwift project as we're building a solar car, but I'm very much on the software side of it. So I'm not about to go across to the mechanical engineers who work with us and say, you should be doing that differently. It's like, I've got no idea, right? And so that's the beauty of the abstraction, is I don't have to know. And so when we've got these C and H files, what we can access from the H file is the functionality that's been provided to us in a nice, easy format. And I don't need to know how it works. I just trust that the C file has been implemented in a way that it does what the H file says it should do. So sitting in the driver's seat of a car, I don't need to know how the engine works. I don't need to know the details of a 4-stroke internal combustion engine. I don't need to know the details of a fuel-air mixture or a power steering system or anything like that. And the power steering system may have been implemented with electric motors or hydraulic motors or other things. I don't know. I just trust that it works. And so what we can see is I steer like this, and I can steer multiple different cars like this because they're similar functions, but underneath all the cars might be built in different ways. And so that's what we're getting now with abstract data types, is we can operate it without understanding what's underneath it. And from the other perspective, when we're creating these things ourselves, when we're putting the information in the C file, what goes in there is the ability to provide the functionality, but everything goes across this interface of the H file. So the H file says these are the only ways the main file can do anything in the C file, and the C file must provide those functions. So this is why in your assignment, Beats by CSE, we have locked down the H file. So we've locked down the H file to say our main function is going to expect certain things to happen. We're going to ask you to implement those things in the functions that are in the C file, but the H file is kind of locked in place. It says this is the interface between which your code and our code in the main need to talk to each other, and if we both write our code the right way, then it's going to be fine. So if everything in the C file is written to make sure that the functions in the H file are faithfully implemented, then anything in the main file that calls those functions expecting them to do certain things is going to get the results it expects. So this is a really nice construct, and you can see already how this starts to let us work in teams really nicely. So when we get together as a group and we figure out, okay, these are the things that we need, we can lock down our H files to say, okay, these are the things that the person writing the main program needs to have happen, and someone else in the team is writing the library, and they commit to saying that each of these functions in the header file will be done in the right way once we've finished it. And someone who's writing the main program says, cool, I'm just going to use those functions. And they can be working at different stages, they can be at different levels of completion, both trusting that when they're both complete, they're both going to access that interface of the H file together, and then have it all come together in a nice way, like that. So we're building up our capability here, right? So it's really funny, because like just over 2 months ago, we were looking at how to store a number as a variable and things like that. And what I love is like now we're getting to this point where, okay, with a bit more training, with a bit more time and practice, we can get to the point where we're actually, you know, working like professional programmers. And so this is what I love about this course, is we can actually show you not just, okay, here's our very first program. We do want to show our very first program and stuff like that. Here are the real basics. But we do want to show you also, it's like, this is a much bigger deal. There's so much more you can do with this, and you don't even need that much time or that much understanding to get to the point where you can start using these things in a way which is really not that different from how professionals with 10, 20 years of training are going to be setting up a project and doing it. So these are the same ways that we set up projects when we were doing large things in C-like languages. There's more languages than just C, obviously, but there are several languages that use this same idea of an interface to be able to separate bodies of code, and that way you can have people working on separate parts of it, and it works pretty well. Someone saying let's just code a car. Yeah. Yeah, a couple of questions there, but I think Michael is there answering most of them. Okay. So, I did mention the Typedef. I should go back into the details and talk about all this stuff, right? So, when we create an abstract data type, in C, we would use something like a Typedef. Other languages might do it differently. Abstract data type is now getting to the idea of the name of this course is Programming Fundamentals. It's more about how to program than it is how to write C. We happen to be using the C programming language for this, so all our implementations are in C. But the idea of an abstract data type really transcends the language. Like, it's something that we're going to use in multiple different languages. Java loves them. The entire field of object-oriented programming uses things that are a bit like this. Object-oriented programming used to be really big, came about in the 80s, and there's heaps of programs that are still using it a lot nowadays. I think we're going to see less of it in the future, but I think it's still worth knowing about the idea of abstraction, because there's a lot of stuff that's really valuable in it nonetheless. I'm not going to go into the details of object-oriented programming here and now. There's just so much to talk about there. But anyway, the Typedef itself is how C deals with this particular thing. It's a pretty simple concept here, where we have a type and a new type name, and they become interchangeable once I've done this. It's not exactly the same as a hash define. So a hash define says one thing becomes another, and it's really specific, where it will go through all of your code and it'll change one to the other. The Typedef is less of a sort of sledgehammer. Like the hash defines like a sledgehammer. It'll go through your code and it will rip out pieces of your code and replace them, in a sense. The Typedef is more subtle, where it says, I'm not going to change anything in your code, but I'm going to allow you to use these things interchangeably. The key then becomes, I can typedef one thing into another thing. So one of the things I'm typedefing here is a beat pointer. So a pointer to a beat structure. So this is one type, the pointer to the beat structure, and the other one is the capital B beat. What we're doing when we're saying that is we're saying that a beat is a type. It may happen to be a pointer to a structure, but since you don't know what the structure is, you shouldn't be thinking about it as a pointer to a structure. You should just be thinking about it as a beat. So you think about it as a capital B beat and use it like it is an object that you can pass around and do things with, and you can pass into functions and stuff like that. Don't bother thinking about it as a pointer to a structure, because you don't have access to the structure. If you include the H file, you do not have access to the structure. You only have the capital B beat. So if you look in the main file in the assignment that includes beats.h, it will never have capital B beat and an arrow after it, so it will never have the arrow looking into the fields inside. It's not allowed to see them. The only things it will ever be able to do is take these capital B beats and put them into functions. So you say, you gave me a function to add a note to a beat. Here we go. Here's the function. I will call the function with the beat. I will never be able to access the linked lists of notes. I will only be able to say, I would like to add a note. Do you have a function that does that? I will call that function, right? So it's very different from the way we were working last week with the linked lists and the battle royale, where we were deep in them. You know, we were accessing the fields inside them, we were changing them, we were moving pointers around, all that kind of stuff. When we put something into an abstract data type, we don't get access to the underlying data. We only get access to this capital B. And so the Typedef helps us a lot as humans to think of this thing as an object and not as a pointer that we can do stuff with. So capital B beat is just a thing that we can use. And when I say thing, I'm intentionally being abstract about this. So it is a concept, the beat, and the concept has properties. So the beat has notes in it, but it does not have an underlying implementation from my perspective. So when I'm looking at the capital B beat, I'm just like, yeah, it's the idea of a beat, and I can use it in these functions, and the idea will be implemented, possibly by someone else, you know? And so this is why we call it an abstract data type, is that we don't know what's in it. It's considered abstract to us. Yeah. So hopefully this is getting through. I realize that I've said the same thing like 4 or 5 times in the lecture talking about this idea. But I mean, it's like one of the weirder ideas that we're going to talk about, because the idea of abstraction says that we're only talking about ideas, we're not talking about code itself. And I think that can be a bit confusing when, especially last week, it was like code, you know, it's like just hardcore coding for like 2 full lectures straight. And now I'm talking about the idea that all that hardcore coding, we're going to hide it. And someone else is never going to see it. They're going to see a clear set of function headers that they can use, and that's it. But the beauty of that is that you don't force your colleagues to understand every single line of code you've written to be able to use it, and they can use it to full capacity without understanding it at all. And that's like one of the powers of this idea of abstraction. Okay, so the typedef goes in the header file. I'm going off on tangents here, but the slides will keep me back on track and make sure that I cover exactly everything that I planned to cover. Okay, so when we put the typedef, we put that in the header file, and I think I've already said everything that's on this slide. Yes, you can see a type without knowing what it is. The details are hidden in the C file, which is not included, so the main file will never see what's in the C file. But when it's compiled, they'll all be linked up together, so that when I call the function in the H file knows where the C file implemented that function and goes and runs that code. So it'll all end up linked up together after compilation. But we still, when we're writing the main file, we can only see what's in the H file, and those are only the things we're going to use. Yeah, and so this is all stuff I was talking about, the idea that the header is the controls, I guess, and then the implementation is like the engine itself that's doing things. And so we don't look at the car engine while we're driving, we only look at the controls of the car. Let's look at our first example of an abstract data type. This is a good example because it's one of the standard computer science data structures that we use. It's a queue, and the queue is particularly good because it's something that we can understand, because it's something that humans do as well. So if we're going to get some food, going to get some takeaway or something, back when we could actually go in person and get takeaway and not just order it and get it delivered, we might stand in a queue. So we might stand waiting behind other people for our turn to get served. It's a pretty familiar concept, because we all know the idea that whoever's been in the queue the longest is the person that gets served next. So they're the person that ends up at the front of the queue. So they've been there from the back to the front, and everyone lines up one after another behind them. And so it's always whoever was there first gets served first. Whoever just arrives goes onto the back of the queue. So if we were to look at objects like this, we've got the oldest object here, and if we were to remove anything from the queue, So that's like someone's being served, they leave the queue. The oldest object is the thing that gets removed. If we're going to add anything to the queue, it goes on the new end of the queue. So it's like, okay, new stuff goes on one end, old stuff gets removed from the other end. So, pretty simple concept. This is an idea, right? So I have not said anything about code here. What I'm saying is this is an abstract. It's a concept of something that should do something. And that's all I'm saying about it so far. But you can see how every computer program must start with an idea like this. Every computer program must start with an idea of what it's for and what it should do. And so a queue is there to organize objects in such a way that if I just throw objects at it, I'm going to get the objects back out in the same order that I put them in. So the oldest object that went in is the first object that gets pulled out. They have a sort of an acronym that they use for data types like this, and it's called first in, first out. So the first thing that was put into the queue is the first thing that will come out of the queue. So the first person that joined the queue is the first person to get served, that kind of thing. So this is the idea of a queue abstract data type. Important to note that I haven't talked about any implementation here. I haven't talked about how this is going to be built or anything, but even without building this, I have a set of rules. So the first rule was first in, first out. Second rule is anything that gets added to the queue gets put at the back of the queue. So there's a few things like that that I know are always going to work. The queue being an idea means that I have not said anything about arrays, I've not said anything about linked lists, I've not said anything about pointers, loops, or anything like that. So the queue is a structure, but not a struct. You know, we don't have a struct yet, we don't have any ideas. Sorry, we have ideas, but we don't have any ideas about how it's going to be implemented. So the thing is, if we were going to make an abstract data type for a queue, we could have a header that says how the queue is going to be used. So we can have a header that says, all right, I need a function to add something to a queue, I need a function to remove something from a queue, and the rules underlying the adding and removing are going to be implemented somewhere, but I haven't done them yet. But I have certain expectations of how they should work. I have the ability to create a queue, I have the ability to destroy the queue, that kind of thing. And the implementation, so this is me putting together the idea of a header file. The implementation that might happen in the C file could be anything that whoever's implementing it wants it to be. So I could say, yes, someone else writing the C file could store the queue in an array, or they could store it in a linked list. They could use structs or not. They could use their own memory management, however they want to do it. And so I don't have any rules about specifically how that's going to work. So, what's the time? Actually, no, good time to do this now. Is there... That's all right. I think Tom and Michael. The fact, if I look over there and I see the moderator text on everything, then I'm just going to assume they're answering all the questions. Okay, we're going to go on break. But before we go on break, I wanted to talk about a couple of things. There's lots of different programming languages. And one of the reasons why we're teaching you C at the beginning is historically C is quite significant in the development of programming languages in general. So some of the big languages out there in the world, I mean, especially Java. In industry, Java, I think, is the most prevalent language in existence right now. I don't really want to say that because I don't know for certain. But I know from a lot of friends that are working in big business enterprise level stuff, a lot of the stuff is done in Java. And if we're looking at web-based stuff, a lot of the stuff is done in JavaScript, which is a kind of cut down version of Java, a simplified version of Java that was made just to run in web browsers. Ironically, JavaScript was made nearly as a throwaway idea for someone to just get a subset of Java working in a browser, and they never intended it for long-term use. But it worked well enough that everyone just started using it, and now it's become a standard. And I think it's one of those things where someone's like, that was not supposed to become a standard. that was not built for longevity. So if anyone does any work with JavaScript, you'll find that there's weird things in it that don't make any sense, and that was from people just going, "Oh, we'll just knock this thing up in a weekend. It was never intended to continue any further." You'll find that out if you ever start working with it. What I want to say is that there's a lot of programming languages. So I don't know how many I know how to code with. Like, I mean, to be really, really honest, in terms of languages that I can genuinely code quickly in, I can only do it in, say, 3 or 4 languages. And I know other people who are happily able to code in like 9 or 10 different languages. But I also know other people who are like, no, I got one. I got one. I'm really good with that one, and that's it. So it depends on your situation and things. But what I want to say is that the way that we're teaching things, and this comes at a good time because it's while we're talking about abstraction and things. We're talking about all of these languages do the same thing. All of these languages will translate our high-level ideas, stuff like a queue, into something that our computer can understand. So once you learn more than one language, you should get this concept into your head. I mean, you maybe don't have this yet, but sooner or later you will get this, that what you're trying to do, so what the ideas that you have that you're trying to implement, you're trying to get the computer to carry out these ideas for you. Those are the important things. Those are the fundamentals of what programming actually is. So that's you learning to communicate with computers. Which language you communicate with computers in will change. It'll change over time, the ebb and flow of what companies are doing and what research is doing and stuff. So you're always going to be shifting languages, but as long as you keep the fundamental ideas of what you want to do in your head, you'll be able to do them with different languages. So if I was to say to any of you now, loop through an array for something, or loop through a collection of data for something, I think with only like a day or two of sort of reading up and studying, you could do this in Python, or you could do this in Java or other languages. You just need a little bit of time to figure out, okay, what are the analogs? What are we actually sort of using to transfer our knowledge? Anyway, I've just talked through the break time slide instead of actually having a break. So let's take a break. And 9:57 now. So let's come back around 10, and we're going to start building up an actual abstract data type from scratch. So I'm going to show you how the header file drives the development of how this thing works, and how our main file is going to access the header file, that kind of thing. All right, so let's take a break now. Come back in a few minutes. Alright, we're back. So, what we were going to do now, let me make sure I didn't have more slides, and I'm pretty sure my next slide is going to jump into the actual creation of the queue that I was talking about. So, building an abstract data type. What we need to think about when we start building something like an abstract data type is how something will be used. So we're not going to think about how we're going to build it. So we're not thinking about whether it's an array or a linked list or something like that. We're going to think about what this thing is supposed to do. So what functionality should it provide? So I have a few functions here that I think this thing ought to have. So to have an abstract data type, I need to be able to create it and destroy it. So I need to be able to say, I want to make one of these and I want to get rid of one of these that I've made. When we're thinking about these things, we can already think in the back of our head, it's like, one of those is going to allocate memory for this thing and the other's going to free the memory for this thing. So we think, okay, cool. That's a good thing to know, is that underneath this, we're going to need to if we're going to store data in this thing, then it needs to store data in computer memory. So these things need to be created and destroyed properly. So we need functions for those. It's a queue. So a queue is a collection of objects. It's a collection of identical structures. And it being a collection of identical structures means I want to be able to add items to this queue, and I want to be able to remove items from this queue. Doing that is going to have particular rules. So I can only remove the item from the queue that's been there the longest. And if I add something to the queue, it automatically goes onto the back of the queue. So those things are things that I need to think about. Another possible thing that I might want to do is to count how many things are in the queue. And we'll see if we get to that today. We'll probably get to it. And the reason why we get to that is that maybe we can't necessarily remove something from a queue if there's nothing in the queue. So if there's no one waiting and I try to serve someone, then there's no one there, right? So we will use something to say, we're only going to serve people if there are people there to be served. If we start with this is pretty basic. This isn't too bad. This is something we can probably do in an hour in the lecture. We'll see how we go. But also this is going to show us how the abstract data type works. So here's a header file for a queue. I'm going to hop over to VLab where I've copied some things over already. You can copy these things over yourself because these are exactly the files that I put in the lecture section earlier. So I'm just going to open my Gedit window with both of these files so we can have a look at them both. So abstract data type demo here, I'm going to create a queue for ice cream. So what I'm doing with the structure here is I am including queue.h. The difference between the angle bracket and the double quotes. The angle bracket is us saying to our C compiler, I'm pretty sure you've got this one. So you have this file somewhere, and I'm happy for you to just find this file. The double quotes is saying, this is my file. So double quotes is actually saying, this is literally a file. So this is going to be in the same directory where I'm compiling this thing. Look for this same file. You can actually go to other directories in this as well. So if I did something like ... goes up a directory, and I could have let's just name it entirely. I could have something like libraries queue, and that would be going up a directory into a different directory called libraries and look for a file there. So the double quotes allows me to say, okay, this is literally a path in my file system to find something. And you'll actually see this if you ever get into like open source programming, Linux programming and stuff like that. There'll be a whole lot of like ... /lib something. So lib is like the short form for a libraries folder. So that'll often happen where it's like, okay, go find the lib directory and do this. So standard input output C library, we don't have that file. This compiler has that file and knows where it is. Q.h, we do have that file and we do work with it. I've started the code here. This is not going to work yet. I'm calling a function called qcreate. I have this idea of capital Q, so we should look in the H file and see what the H file is providing for us. So I've written some stuff here. This is actually from a while ago. This is from a whole year ago. this header file, because the header file was set in stone in such a way that I've been able to teach this several times, and I've written a new C file every time I've done it, but the header file never had to change. In fact, I just edited the main file. I could have left a whole bunch of code in here and it still should have worked because the header file hadn't changed. So let's look at what the header file has. If I just sort of scroll up and down through here, you'll see that a whole lot of this stuff is comments, because a header file is something that we consider to be a very human readable file. So it doesn't have a lot of complicated code in it, but what it does have is explanations for everything that it has in it. So, for example, here we have a typedef. So the typedef is saying, I have one type, but you're going to see it as another type. I think people are talking about the assignment. All right, no, I'm not gonna talk about the assignment right now during the lecture. I've got other things I need to talk about, but you can talk about it there. I don't know if you can hear that. Chicken was just saying hello. Hello, chicken. Your weekly dose of small cat. There we go. I'll put her back down. Okay, so the typedef here says I have one type. Now remember that when we have a pointer, even though the pointer is attached to the thing afterwards, this, what I've highlighted here, is one type. So it's a pointer to a QInternals struct. So somewhere there's a struct called QInternals, and it's going to be in our C file. We haven't actually made it yet, but we will be making it. But what we're going to do is we're going to call it a Q. So we don't know what the internals actually are. All we know is that we're going to use this thing called Q. And then through here, you can see all the types that we're using and all these other functions are the capital Q, because I don't really want to get confused here in thinking about pointers, because it's a pointer to something I don't know about, so I can't really access it. So I just use it as a capital Q. So when I call Q create, I get given a Q. When I call Q free, I need to give it the Q that's going to be freed. If I want to add something to a Q, I need the Q and an item. So it appears here that the item is going to just be a number. So as you know, usually when I'm doing examples, I'm going to keep them pretty simple. So I'm just going to store numbers in the queue. When I remove an item from the queue, I get given the number of that item. Obviously, I have to say which queue I'm removing something from in case there's more than one queue. If I want to check the size of the queue, I can put in a queue and I'll get given back how many things are in it. Okay, so from this, I know that my queue is going to have a certain kind of functionality. I don't know exactly what that functionality is, and I haven't spoken about it yet, but I know that these are the things that my main file or any other file that's including my queue.h is expecting to be able to do with a queue. Alright, so there's the header file. What does our header provide and not provide? I put the not there to be specific about what it can't do for you. So the standard idea of what's in a queue is we can join the end of the queue, or we can take something off the front of the queue. Note that we cannot, through any of those functions, access anything else in the queue. So we can't actually say who's second in line, who's third in line, or anything like that. With the basic queue functions, we're not supposed to be looking at anything that's second or third in line. We should only be looking at whatever's first in line at that point. We can also only serve one person at a time. So we say, okay, you can remove one element from the queue. These things are in order. You can't just say, I'm going to serve the first 3 people all at once. So you can only do things in order. You can only take the first thing off the queue. Note, we are also not allowed to look through the queue. So there's no way, given those functions, that we can loop through the queue. We can only add things to the queue or remove things. So you can see how, if this was a linked list or an array or something like that, I've limited my access to it. So I've limited it to saying, no, you can only add something or remove something. And so what that does for us is it gives us rules and safety. So the rules say you can only do things this way, but if you are just calling the functions for this queue, you will never do anything wrong with this. Oh, it's not entirely the case. You still could, but there are certain types of wrong that you can't do to this queue. So you can't accidentally pull something out of the middle of the queue. You can't accidentally add something to the queue so that it gets to go earlier than in the time frame that it should do. So this queue is going to be quite strict in how it works. No one gets their ice cream without queuing up for it. Although at the moment you have to get your ice cream delivered. But anyway, the header protects us from accidentally doing things wrong with our data. Okay, so Q.C will then implement the functionality of what's in the header. So each of the functions that's in the header will be in the Q.C. This is really, really similar to when we're doing things in a single file and we had our prototypes up the top, then our main function, and then our implementations underneath. So when we had the prototypes up the top, that's like the header file. And if you think about it, the hash include of the header file is nearly going to paste those, hang on, here, these function prototypes here in the H, where we do include Q.H, is functionally similar to me taking this and just copying this, and instead of this include, just pasting it there. So if I was going to do this in a single file, I would have this. So I have the function prototypes, and then I'd have the main that used them, and then underneath here I would have whatever's in the C file would be down here. So it's nearly like I've stripped out these parts so that I'm not in one massive file, but I'm in separate files. I'm just going to Control Z all this other stuff that I've just done here. All right, we'll go back to the way we were there. All right, I copied that, not cutting it, so that's okay. Yeah, so we're back the way we are now. So this hash include is nearly like, yeah, just grab everything from this file and dump it in there. So this way my main knows what all these functions are. Okay, so if we're going to write the Q.C, that means we are now thinking about what the actual implementation is going to be. So if I'm thinking about what the implementation is going to be, I'm going to need to think about exactly how it's built. So what structures I'm going to use. I'm going to start with a linked list. The reason I'm choosing a linked list for this implementation of a queue is because I'm working with either end. So I'm adding things to one end and I'm removing things from the other end. That works really well for a linked list because I've got the idea of this queue can grow and shrink, but it's always going to have two ends, and I can add to one end and remove from the other. Adding to one end and removing from the other in an array is really kind of fiddly because we have two ends of the array, but if I keep trying to add something to one end of an array and I keep trying to take something off the other end of the array, I'm going to have a really weird setup because the array is a fixed length and I'm trying to move this data through. So I find that if I was to implement this with an array, I'd need to do some fiddly stuff with it. So I'm not going to bother doing it with an array. I'm going to do it with a linked list where I think the insertion or removal should be reasonably easy for me. And so this is the kind of thing where I've now just changed hats. So I was the person specifying what we were going to do with the H file and thinking about how it might be used in the C file, and in the main file. And now I'm hopping over to the other hat, and it's like, now in the Q.C file, how do I provide for this? So let's start with a linked list, because I think that just from my experience of knowing how linked lists and arrays work, I know I've got a collection of data, so I had to be one of the two from what we know so far in 1511. I think linked lists are going to be easier for us to use here. Also, I just wanted to do linked lists again to show you, so it's just like sneaking in some more demos. I don't think you need more demos on arrays right now. Having said that, next week we are going to do recaps on things. We're gonna revise a whole lot of the course, so we're gonna go back and look over all of the concepts and at least remind everyone of everything. We'll talk about that later. So Q.C is the implementation behind things. Let's look at the implementation behind the Typedef. So I said that here in the header file we had a QInternals pointer, so a struct QInternals pointer. So I know that there's a struct that points at a Q. this is going to be the structure that governs the list. So it's not going to be just a pointer to the head of the list, it's going to be the pointer to a structure that manages the list. Now, you've seen this before. This is a really similar setup to something like a beat. So a beat manages a list of notes, and here we're going to use a queue-internal structure to manage a linked list of queue nodes, I guess. So let's create a new file. I'm just going to clear that. So I've now made a queue.c. So I've got a queue.h here and a queue.c. So for the queue.c to work with the queue.h, I want to include the queue.h. So this is me saying, I need to know what all of this stuff is so that when I implement it, I know that I'm matching up to these things correctly. Implementation of a queue, demonstration from lectures in April 2020. All right. I don't actually need to put much in the way of comments in a C file because the C file is linked to the H file, and the H file has a whole lot of the details here. So the structure that I'm going to build up here is something that you will have seen already because it's set up in your beats.h and your beats.c file. So if I have a queue internals structure, make sure that I'm spelling that the same way that I was there. Yes. Queue internal structure is going to have something in it. But what I might want to do also is, did I call it a node or a queue node? Queue node. Queue node's a better name because it's really specific. A queue node is going to actually just be a linked list node. So if this is a linked list node, it will have some kind of information in it as well as a pointer. So let's do the next pointer in it. This is the pointer that will aim at another node in the list. So this is actually a linked list node, and it will contain some information. So for the moment, just an integer. You know, and you've seen other linked list nodes before that can contain other kinds of information. For the moment, we're going to keep the queue simple without putting a whole bunch of information in it because we're learning about how to build the queue, not about how to store specific things in it. William's asking if we're at the end of the course content. We're not at the end of the course content, but we are pretty close. I mean, we're week 9 out of a 10-week course, so we're pretty close to the end. Today and tomorrow, I am going to talk about ADTs, and I'm going to talk about queues, and also ADT short for abstract data type, by the way, the whole topic of today. Abstract data types is the last thing. And then next week is going to be a recap of the course, talking about how the exam's going to work and things like that. I was thinking about maybe throwing in some extra topics that are not going to be examined, but are definitely going to be used later in your computing career. But if I'm going to do that, I'll do them in off-timing lecture streams rather than putting them in the official lectures. But we'll talk about that later. We'll see if we have time as well. Okay, so the queue internals is a structure that manages one of these. So in order to manage one of these, it needs a pointer to the head of the list. So we have this structure. This structure governs a set of these. You might be looking at this and just going, well, if this is just a pointer to the head of these, why do you bother having another structure here? And the reason why we have another structure here is this head pointer could be null. And if it's null, and I just said that, for example, I did this was struct pointer to a queue node, and then it was null, it would make these things really complicated. Because then if I'm passing in a null pointer into these, then there's a whole bunch of other fiddly stuff I have to do. Whereas if I can guarantee that this thing always exists, but it might be holding a null pointer, then I can always work with this struct, and it's never something that's potentially null. So it's kind of nice to have this thing controlling access to this. So this is my struct, and this struct goes along with this typedef here. So that's like what we've got here. So to create a queue, I am going to need to memory allocate the queue internals so that it exists, and the queue will start off as an empty queue. So what we do is we take queue create here. I'm going to copy this and implement my first function. Note something interesting: the queue.c is not going to have a main function in it. Specifically, definitely not going to have a main function in it, because the queue.c is going to be used alongside a program. The program itself is going to have its main function, but the program is going to be including the queue.h, which is going to be using the queue.c functions. But if I was to put a main function in here and tried to compile it with something else, then there'd be two main functions. My compiler wouldn't know which one of these is the one that the program starts with, and so that would be an issue. So what the queue.c file does is it provides function implementations for the queue.h. Queue.h provides those functions to the main.c. The main.c is the thing that actually has the main function in it that says, okay, I want to use these functions in this order. I want to do this, then I want to do this, then I want to do this. Whereas the queue.c is just, okay, here's a collection of capabilities, right, that we're going to have. So that's why the queue.c won't have a main function in it. Okay, so if I want to create a queue, first thing I need is to build up this structure. So if we're talking about it in your assignment 2 terms, this is a beat and this is a note, for example. So I need this thing to be created, and then there to be a list of the queue nodes inside the queue internals. So the first thing is I make a new queue internals. I'm going to call it new queue, and that's going to be a memory allocation of the size of this particular struct, queue internals. Because it was a pointer to queue internals, it should be memory allocated the size of the queue internals. This is pretty small because the only thing it holds in it is a pointer. This is not allocating the memory for all of the queue nodes yet. This is just allocating the memory for the thing that manages the queue. So I now have a queue manager. I could have called that queue manager. I'm going to leave it as queue internals in the moment. So I have created a queue internals. It does not have a queue yet, but if I say queue internals head, so I say the head of the list, the pointer that is inside the queue internals, for the moment I don't have anything in my list because I have not called add to queue or anything. Is it called add to queue or queue add? I've not called queue add, so this queue must be empty to begin with. So I'm going to say that the head of the queue is null, so saying that this is an empty list. I don't think I need any more information than that, other than to say that I need to give back a queue to say that I've finished here, so I can return my new queue here. So note that I made a queue internals pointer here called new queue. I wanted new queue to appear to me, oops, I'm about to move that, as a queue internals pointer, because I was about to use it like a pointer. However, when I return it, whatever's using this function, the main program that's using this function, is going to see it as if it's a capital Q queue. And that is because in this typedef, a struct queue internals pointer and a capital Q queue are seen as the same type of object. So we can interchange them both depending on how we want to look at them. When I'm in my queue.c, I'm very likely to look at these as if they're struct internals because I'm going to be poking into the struct itself. when I'm in my q.h and my main.c, I'm never going to refer to them as struct internals pointers, because neither of these two files knows anything about what the qinternals struct is. So it shouldn't be calling it that, because you might accidentally start trying to use it like a pointer to a struct. Okay, so that's my qcreate. All it does is it allocates it, sets the list to be empty to begin with, and then gives back the access to it. Oh, opening up some PTSD for Tyler there. Yeah, a lot of learning about linked lists is learning about trying to access null pointers by accident. Yeah, Cooper, I'm totally with you there. The word Q gets much weirder the more you look at it, because it's just phonetically just makes no sense at all. I think it's just one of those things that comes from another language. Is Q French? Just looks French with the collection of letters like that. I don't know. But it doesn't feel like a word that sits well intuitively in your brain. Okay, we can create a queue. So let's think about adding items to the queue. So what we want to do, if we have a linked list like this, and so Q is French, so I'm going to say. But William is also saying that English makes no sense, and I think you have a very, very good point there. Overall, the idea of the language English... Sorry, someone poking the back of my chair. The idea of the whole language is very, very strange. But I mean, that's like, I think most human languages, they're not invented, so they don't come out of like a lab somewhere and someone says, I have invented an entire language you can use for everything. They're just sort of grown. So stuff just attaches itself to them depending on how things work. That's why so many of our the words that we use in English are actually German and French, because over the Middle Ages there was a lot of relationships back and forth between Germans, French, and English and stuff, and so there'll be heaps of words that have just sort of snuck in, and Latin as well. But we digress. So if I want to add something to the queue, I have decided that I'm going to use my queue in this particular way. And I say I have decided because that's actually how it is. If I wanted to, I could have the head of the list at this end and the tail at this end, or I could have the head this end and the tail this end. So long as when I'm finished with my implementation, it provides for the rules of the queue correctly, then I can do anything I want inside. Like I was saying, I could have done this with an array if I wanted to, it just would have been more complicated. So I've decided that the head of the queue is the oldest object, in which case the end of the queue here where the null is the newest object. So what I would like to do is I would like to, if you're trying to add an item to the queue, it goes on the back end. So I'm going to loop through all of these objects until I get to the end, and I'm going to say this is where you add an element. So each time you add an element, you add it in the place of where this null pointer is, and the null pointer kind of moves along, or the pointer off that object becomes a null pointer. So what I'm saying is we're going to add at the tail of the list, and the head of the list is going to be the oldest objects that we're going to remove from the list. So, simple way that I can think of doing this is to loop through to the end of the list, and then add the element onto the end of the list. This seems a little bit more work that I necessarily want to do all the time, because like, why would I want to loop through the list every time to add something onto the end? Why don't I instead keep track of the end of the list? And this is another benefit of having something like qinternals, that I could have another pointer in the qinternals that says this is the end of the list. So I have a pointer to the start of the list, I could have another pointer to the end of the list, and I can say always add on there. And that way I might get a simpler way of adding something to the end of a list, so long as I'm always managing where the end of that list is. I'll show you how that works now. I'm going to add a pointer to my qinternals called tail. So it's still a node pointer, but this one doesn't represent the entire list the same way the head, because the head has access of the arrows that are going to go in that direction. Maybe I should have flipped this diagram around. Oh, doesn't matter. You can still understand it because the arrows are going in a certain direction. But I can have another pointer here called tail, and tail is going to point at the final object in the list. So let's just have a quick look how I'm going to do that. So I now have a pointer here that might point at the end of the list. For the moment, the head and the tail are both not pointing at anything while my list is empty. So I need to actually set that up. QInternals tail is also null. So on an empty list, I'm not pointing at the last element of the list because the last element of the list doesn't exist. So if I want to add something to the list, every time I add something to the list, the tail pointer will point at that. So the newest object will always be the tail pointer. So every time I add something, I need to make the tail pointer point at it. So if I'm going to add something to the tail, I have a new object here that I've just memory allocated somewhere, and I'm going to take the final object of the list, which was the tail. I'm going to get its next pointer, which was null, to point at the new object. Then I'm going to get the new object's pointer to point at null because it's the last thing in the list. So this is just normal insertion at the end of the list. But then I'm going to move my tail pointer to keep pointing at the end of the list. So that way, the next time that I'm going to insert something at the end of the list, I say, okay, look at what the tail pointer is, and then just insert after that, rather than looping through everything in the queue to find it. So this is me kind of sneaking towards the idea of me using an extra pointer in one of my structs in order to use less processing time in general, because I won't have to go through everything to find something. So I'm sneaking in a little bit of optimizing my code to make it nicer. However, it's also making it more readable because there's just going to be less code that I'm writing, less looping going on as well. Okay, so here's some code for adding. I won't go necessarily through this slide. I'm going to type the stuff in about this. So if I'm going to add something to the queue, we're going to look at over here how we've been asked to add something. So you can see I'm not even going in order here because I haven't done my queue free yet. But what I'm going to do is build up some functionality, and then we're going to look at the memory leaks and fix them up in a second. But what I'm going to do, actually, I'm not even sure if we're going to get time for that. We may not finish this entire thing today, but I'm definitely going to get some adding and removing going in. So take my queue add here and say, okay, I'm going to now create this function. Also, I should remember every time you have a function, you should have at least some comment in it. Create a new empty queue. Yep, it's weird in my typing as well. Return the queue pointer to the queue internals. Just being really explicit about what that's going to do. I don't have to put a lot of detail in there. That's just to remind me when I'm working my C file of what this thing does, because they should be documented here in the H file. I mean, this is pretty thinly documented here in the H file. Often you'll have more information, but this one doesn't need that much information. Okay, so creates a new empty queue, returns the queue. This one is going to, I'm just going to put some white space at the bottom. I have this thing, like, especially when I'm lecturing, I want to work in the middle of the screen. I think it's an instinct from working on projectors all the time. Okay, so this one is add an element to a queue. You know, it's not just add, because we're getting the integer item, so it's actually create and add an element to the queue. Okay, if we're going to create an element, then we need to create a queue node. In order to create a queue node, I'm going to need to memory allocate it, which means I need to maintain a pointer to it. So I'm creating a pointer to a queue node here, creating a pointer to it. I'm going to call this new node. I do like calling stuff new stuff when I'm creating it in a function, because it reminds me of which variable inside this function is referring to the new thing, in case there's multiple, because could be. So the new node that I'm creating is a memory allocation of a certain size, and that size is going to be the size of a queue node. Ooh, that's not correct code. I just realized, I don't know if anyone has said that here, where anyone else picked up on that I was, I can't just say queue_internals. Queue_internals is not a variable type, but struct queue_internals is a variable type. So I just noticed that as I was doing this one. So struct, oh wow. It's like, it's gotten so weird to me, I have lost the ability to type in the word queue. Especially as I'm going faster, and I'm just sort of typing stuff in. Okay, so, memory allocating the amount of memory necessary to make a queue node, maintaining a pointer to a queue node called new node. So this gives me new node, which is a new node that's in memory that I've allocated. Okay, so if I've got that node, I now need to add that to this queue. So there's two cases here. One case is if the queue is empty, and the other case is if the queue has some elements in it. So I can split those up into an if-else. So if the tail is null, then I'm not going to say elements. I'm going to say there's no nodes in the queue. So if there are no nodes in the queue, then I'm going to need to kind of create the queue in a sense. Else there are nodes in the queue. Just making that explicit so I can remember what's going on. We might do the else first, actually. So if there are nodes in the queue, this is reasonably simple. So I know that tail, the queue's tail, is currently pointing its next at null because I know it's the final element in the queue. So I can say that I've created a new node, queueTail next. So this is where I'm actually going pointer to pointer to pointer. So queue gives me one of these queue_internal structures. Then I go inside there with an arrow to get to its tail. Tail gets to me to a queue node, which is one of these, which then has an element, a field in it called next. So I'm going to say here, go to my queue, go to my tail of the queue, which is a node of the queue, go to the next pointer from that tail. So people were asking me earlier about can I go head next next. This is a similar thing where I'm following a chain of pointers through things to get to a certain point. Williams asked me if I remembered to include standard library. I did not remember to include standard library. So let's include that now. The reason I need standard library is I've just called memory allocate and size of. Both of those things are from the standard library. I'm going to need them. I'm not necessarily printing anything out here, so this might be one of the very few times where I'm not using standard input output. So the standard input output is going to happen here in the main file, but the q.c is not providing any printing. In fact, q.h does not have anything that appears to need printing. So there's a chance I won't even use the standard input output library here. Ah, good question, Patrick. This is basically creating something where we can determine our own rules with how the data type works. Very much so. So I'm saying that, yes, this is a linked list, but this is my linked list, and my linked list says 1 in, 1 out. So well, not 1 in, 1 out, the first in, first out. So whichever thing has been in there the longest is the thing that can come out first. Okay, so if there were nodes in the queue, then I can change the next of the tail. So this is currently null. The tail's next is always going to be null. So the tail's next, instead of being null, it points at new node. So now it points at this new one that I've created. Having said that, I should actually go back up here and say this thing has no information in it for the moment. It needs some information. So my new node data is going to be equal to the integer that I was given, which is called item. I also know that if I'm inserting this new node at the end of the list, then its next pointer will be null. Because no matter what happens, even if there is or isn't something in the list, my new node's next is always going to be null because it's always going to be the end of the list. So this is me creating the new node and giving it its information, and this is me figuring out which of the two cases under which I'm going to insert this node into the list. So if there were nodes in the queue, then I can just get the tails next and point it at the new node. New node's next points at null already, so that's fine, we're done. If there were no nodes in the queue, so if the tail was null, it means the queue is empty. I mean, the head and the tail will both be null if the queue is empty, but I'm checking for tail because I'm concerned with tail at the moment because I'm adding at the end. There's no other reason tail would be null if the list had any nodes. So if the list had any nodes at all, then the last of those nodes should be the tail. So I'm trusting myself here in everything else I do with adding and removing and stuff like that, that I'm going to maintain the idea that tail will either be pointed at the last node in the list or it'll be null. And it's only null if there are no elements. So tail equals null means there's no nodes in the queue. So if there are no nodes in the queue, then I am giving us the first node, the first and last node, because if there's no elements in the queue and I insert a new node into the queue, it becomes the first and the last element. So if it becomes the first and last element, then the head pointer points at it, but the tail pointer also points at it. So now I have the head and the tail are both pointing at the same node if there's only one node there. So this should be everything that I need. I've created the node with its item and its next is null, and I've said if there's nothing in the list, it becomes the only thing in the list, so both the head and the tail. But if there were other things in the list, then this thing just joins on the end. So the tail's next, which used to be null, now points at the new node. New node's next points at null, still a complete linked list. So you can see how this code is pretty thin. There's not much I had to do here. Just create the node and then either create a new list with just this node in it or add it to the tail. So pretty simple code for just adding something to the end of a list if I have a structure that manages the list that keeps track of the tail. And I need to make sure now that I'm careful with the head and tail pointers to manage them correctly. So I had to do this here with the create to make sure I was managing them correctly, setting them both up with values. When I'm removing lists, I'm also going to have to do things like that. Removing elements from the list, which is, I think, what we're going to do now. Before I go on, I'm going to at least compile this. I know I can't do much with this yet because there's not much capability here, but I could at least go creating the queue for ice cream. Let's make an integer. I'm just going to have a number 1, and I'm going to say printf adding person to the queue, and the person is going to be I. Then I'm going to call the function for add called QAdd. QAdd, what did it take first? It took the queue and then the item. So the queue is called ice queue because it's a queue for ice cream. And then the number we're putting in is 1. I'm not going to get much out of this testing, but if something breaks, then I'll see it, at least, because now I'm calling the two functions that I've made. So I'm calling, I need to call the actual function. Yes, I need to spell that correctly in order to call it. So I'm calling the function to create a queue, and I'm calling the function to add one item to the queue. I can't verify that this is correct or not, because I actually have no way to look through the list and see what's in it. But at least I'm going to say these functions that I have implemented here, let's at least compile them and see if they do something. So I'm going to clear all of that. And so to compile this, I need to compile all the C files that are going to be used. So I need to compile the main.c and the q.c, and I'm going to make a single program called qdemo. Oops. Where have I done this? Okay, q.c at 22. This is me doing this again. Q internals. I've got a pointer to new q, and I've called it q internals. I've called it its type instead of its actual name. Oops. This should be new q, and this should be new q. I was getting caught up in the abstract idea of what it was rather than what it was called. So that hopefully gets both of those. Oh, and I've also done this thing here where I've just gone tail. I'm just thinking, so this is me kind of thinking out loud and just typing stuff in. I'm just going, yes, the tail of the list that I'm looking at. And my program's like, what do you mean the tail? Like, you just use the word tail. It's like, no, I meant the tail of this queue. I have this habit of sometimes programming conceptually, like I'm just throwing stuff up on a whiteboard instead of correcting. And it's so funny because I was corrected here and here, but I got it wrong there. Okay, so a lot of that syntax stuff, hopefully that will be fixed there. Okay, good. Probably working. Who knows? Can't tell for sure just yet. And I can run qdemo, see what happens. Okay, some good news. I can create a queue and I can add person 1 to the queue. Whether or not those things actually did what they said or not is another story, but for the moment it got through everything and finished, which means at least none of my functions are stopping. None of my functions are crashing right now. They could later. None of them are getting stuck in infinite loops, although it'd be very hard to get stuck in infinite loops in a program that has no loops. So for the moment I think we've tested enough to continue further to figure out whether things are definitely working or not. So people are pointing out to me all of my syntax errors there, I think. Yes, everyone was pointing out all the issues that I had there while I wasn't watching. Yep. That's really funny. Patrick's asking whether we have to compile one file before the other. No, we don't. We can compile the C files in any order we want. So basically the C files get transformed into a series of sets of instructions based on functions. So your main will be a set of instructions, my qcreate will be a set of instructions, my qadd will be a set of instructions, and then the H file will go through and go, okay, where are those bits? And it'll say, whenever someone says qcreate, go to that set of instructions and run them and then come back when you're done. You know? So they don't have to be in anywhere in particular. The main could be below the qcreate, but it would still run first. And anywhere it says qcreate, you would jump to the other code where qcreate is, run that, and then jump back to the main. So the C files don't mind about the order because all they do is provide a capability, and then when it runs, it jumps between things to run those bits of code. Simply Me Joe is asking, should qtail equals qnode be outside the if statement to make a new tail every time a node is added? This one here, or this one here? I think between these two are slightly different. So this one is assuming that there is nothing in the list, in which case the tail will then point at the new node. Oh, you're right. Ah, well done. Okay, I do have an issue here. So here, I've made the tail's next point at the new node, but I haven't moved the tail pointer. So what I've left out is this tail's pointing at the object, the new object comes in, the tail there has to move to there. You are correct. If I cut that out of there and paste it here, I make sure that the tail pointer always moves to the new node that was inserted, whether or not it's the first node, the only node in the list, or just freshly added to the list. So that would have caused some serious problems later on. We would have ended up losing things from the list. That was actually a pretty major logical error that could have broken things. Especially with 10 minutes to go, that would have been really bad, because I would have been stuck debugging that. We wouldn't have finished the code that we were doing. Well done. Nice work there. Okay, so let's have a look at removing from the list. I'm going to try to get this at least removing. I have space tomorrow to continue working on this anyway, so it's not that bad. But I do want to at least look at removing. So removing from the node, we're going to remove the head of the list. So we're going to take the oldest object, which is the one that the head is pointing at, remove that from the list, have the head pointer move on to the next object in the list, and then the oldest object in the list is freed. So code for removing will look a little bit like this. Let's actually type this in here. So qremove here. Remove oldest node in the queue, the head. Return the value stored in that node. Okay, as you may have seen here, first thing that we're going to do is see if we're trying to remove from an empty list. We have an issue here in that we're supposed to return a value no matter what. There's no value that we can do that's not a valid integer, so there's no value that we can give it that is not a potential element of the list value. So what I've chosen to do here is instead of just saying if you tried to remove from an empty list you get like a 0 or something, but maybe I was storing zeros in the list potentially. I don't want to always be grabbing things like 0, so I'm going to say if the head is null, then we're out. This whole program cannot continue because you're expecting an integer and I can't just pull one out of thin air. So we're going to exit 1 out of this program. So exit 1 is going to say the entire program is going to stop. This 1 is not a 0, so this entire program is ending without a good finish. So if I say if head is null, list was empty, I'm going to give a message. And bail. So I'm just gonna ghost them entirely at this point because there's no way I can get that to work. Otherwise, I could put an else here if I wanted to, or I could actually just not put an else here because this thing is going to end the whole program here, so the only way I'm going to get here is if this wasn't null. So if head is not null, that means head has a head has a node. So what I'm going to do is get the information that I'm going to give back. So I'm going to call it, what did I call it there? Return data? Yeah, sure. Return data is equal to the queue's heads data. I think it was called data. Yes, the data. So I take the first element of the queue's head, take its data, and say that is the return data. I am also going to grab a pointer to the head itself, to point it to the first element of the list. So struct quNode pointer, I'm going to call it, I'll call it removed, because it's a node that's about to be removed. Wait, rem node, removing node, because it's the node we're removing, and it's going to be the node that we're going to have removed as well. Oh, hello there. Sorry, someone just jumped up on my lap. You can come sit here if you want. Can you see her? Oh, you can't see her. Hello. Okay, so the node that we're going to remove is the node that is still currently the head. So what I can do now, since I've kept a pointer to the current head, oh wow, I did exactly the same things I did last time. Strangely enough, I think like myself. So this is me maintaining a pointer to this object, which is this one that we're about to remove. So once I've got access to that one, I can skip the head onto the next object. So this is moving the head to the next object. So I can say the queue's current head should not be the node that we're looking at now. It should be the next. So it should be queue head next. So what this is saying is that the second node in the list should now be the head of the list. This could potentially be null. So if the list only had one element in it, I could now be making the head null. And that's fine, because that's me saying the list is empty. So what I'm saying now, actually I'm going to put some comments in here. Keep track of the node for removal, and then move the head pointer to the second node or null. This has done everything we need in a sense. So we've kept track of the return, in which case we can actually say return the return data. That's the last thing that we're going to do. But before we return the return data, we're also going to free the rem node. So this is us dealing with this final node here. Is we're going to free it and return it, and we've moved the head pointer onto the next. The only issue that we might have here is, as I said before, we want to maintain what our head and tail pointers are doing all the time, because the tail pointer may have pointed at this node. So the only situation where the tail pointer was pointing at the same node as the head pointer is if there's only one element of the list. So if there was only one element of the list, then that head's next was null. And so if I've just made the head move to its next, so I'm saying the head has a next, and the head pointer is now no longer pointing in that node, it's now pointing at whatever its next was. If that was null, so if after I move it to its next it becomes null, that means I removed the final element from the list. If I removed the final element from the list, that means that I have removed the node that this tail was pointing at. So the tail now becomes null. I should put a comment in here as well. We removed the final node in the queue, which means tail is now not pointing at a node. Okay, so this means I should be able to empty my queue down to nothing, and the tail will end up null. What I have done is I've taken the information out of the head, kept a pointer to the head so that I could free it, moved the head pointer along to the next. So in between all of this jumbly stuff here is the ability to remove a node remove the head node while moving the head pointer onto the next element and keeping track of whether I needed to do anything with the tail pointer. See if it's the same as what I did here. I don't think I kept track of the tail pointer in this code here. I wonder if I put this in there later for other issues. Anyway, so let's test our code in our main, and because I have like 1 minute left, instead of typing this in, I'm going to copy it. Alright, I'm going to copy that in here. So what I'm doing here is creating the queue for ice cream, and then having person 1 join the queue, person 2 join the queue, and then person 3 join the queue. And then I'm going to queue remove, which is going to give me integers back, and say who got their ice cream in what order. So if this queue is following the rules correctly, then whoever went in first should get their ice cream first. So let's compile and run this and see if it works. Also, if it compiles, because I'm sure there's going to be... Yeah, I've done the same thing I always do, where I talk about the head and tail of the list without using the actual queue itself. So 46 was the first time I did it. Yeah, this should be the queue's head, not me just pulling out an abstract idea of the head there. Let's compile that again, see if I've got any other issues. Oh, implicitly declaring library function printf q.c. Oh, I did end up using a printf there, which means I need the standard input output library. There. I'm going to compile that again. Note the way that I ignore the errors after the first a lot of the time, just in case that they're just consequences. Line 55, I've used head again. This should be the queue's head. Compile that again. Alright, now we're actually compiling. Are we... Couple of questions here. Richard is asking, why do I return the data? When I remove something from the queue, what I usually want to do is, for example, if it's a queue for ice cream like this, I'm actually serving people in order. So I don't know who it is that I'm serving, which is why my remove is actually not just going to remove the element from the list, it's actually going to tell me which element it removed. So that way, when I've put things in the queue, what I'm doing is I'm kind of serving them one at a time, which means I want to get the information out of it, which is why the remove is actually returning the data that was inside it. Because I don't really know what data is necessarily going to be there, I just know that stuff's going to happen in order. Alright, let's run this. See whether it works. Awesome. Created a queue for ice cream. Person 1 joins the queue, person 2 joins the queue, person 3 joins the queue. Then, as I remove things from the list, they are removed in the same order that they went in. So my queue is following the rules that it should follow. Okay, I'm over time now. Let's wrap it up there. I'm going to talk more about this tomorrow. We're going to finish this example because there's stuff in this we haven't finished here. And I'm going to talk about another abstract data type called stacks. We won't do as complete an implementation, but I will talk about stacks as well. I'll stick around for a little bit because there are questions here, because I went pretty fast by the end there. So there's questions here that I'll answer, but if you've got a tute to go to now, head off to your tute, but I'll answer whatever questions are here in the next couple of minutes. Especially because I think the tutors have gone off to teach tutes, so they haven't answered questions for a while. So people have been talking to each other here. I'll go back to the last time Michael answered something. Let's see. Teresa's asking, I don't know if I've gone back too far. People are saying the if statement condition is incorrect on line 31. Did I already fix that? I'm not sure. Oh, line 31's not even there anymore. Was it this one? If the tail is null? Or was it one of these? I'm not sure where that is. I think I've gone back too far in the comments. Okay, let's see what other questions we've got here. Yep, people are helping me out with my typos. Q head. Did Mark initialize the values for Q data? Did I or did I not? I think in add I did. So every time I add something to the list, the item goes in. So each node's data should be okay because there's only one way to get data in. Patrick's laughing because I keep forgetting to do Q arrows. Yes, I do. Data is in Q add, yeah. But was Q data equals item written? Yes, I think it was. Well, I mean, new node's data was, yep. Item value would be passed into the function. Yeah. Okay. Cool. What's the purpose of rem node? Humphrey's asking this. Okay. So let's go back here into removal because I jumped around into this in this function when I was making it. I made it in lots of different ways. So a pointer rem node here is a way for us to keep track of the head. Let me show you. So, pretty small list, simple. There's my head pointer. So, my intention here is to move the head pointer to the second node in the list. I'll do this so you can see my cursor. Move the head pointer to the second node in the list, and then free this pointer. So if I was to simply remove the head pointer, I would do this, I would immediately lose this node. This node here is now gone because I no longer have a pointer to it and I can't do anything with it, which means I can't free it. I've created a memory leak if I do that. So if before I move that head pointer, I make a copy of that head pointer. So a copy of a pointer aims at the same object as that pointer, and I call that one rem node. Now I have access to this node so that when I move my head pointer along to here by copying the next of this node, I still have access to this node and my head points at this node, which means now I can use the rem node pointer to free this node and its pointer, right? So that's why I needed the rem node. I needed it there to keep access to the one that I was about to skip over. Where was that question? I'm trying to find. I'm just scrolling back through chat. Okay, that was Humphrey's question, purpose of rem node. Richard was asking why I returned the data. I think I answered that one already. Patrick's saying some of the logic in the Q add function might be incorrect. It doesn't make sense to set Q tail next to be equal to new node and Q tail equal to the new node. Okay, let's go back and have a look. So Q tail next equals new node. Let's draw another diagram. So let's have our same list here, and then we have, I'm just going to do them in a different color. So we've got our head here and our tail here. Tail's pointed at the node that points at null. So let's look at the lines of code, make sure I've got those correctly. So just assuming there are nodes in this, Q tail next is equal to new node. So assuming we've created a new node, let's create a new node. I am new tail here. Tail's next points at new node. So tail's next is this pointer, no longer pointing at null. Tail's next equals new node is going to change tail's next to point at the new node. So tail next new node is that line of code. It does that. Then after that, qtail is equal to new node. So tail is this. For tail to be equal to new node, then tail has to be aiming at new node. So tail's no longer aiming at this node here. Tail is equal to new node is going to do the following. And that's what we wanted out of this. So first, we take this tails next to aim it at the new node, and then we change what the tail itself is pointing at. It's now pointing at the last node in the list. That was also pointed at null there. So we're back to being a proper linked list with tail pointing at the last element of the list. So hopefully that makes sense. So qtail next should always be null. Yes, but there is a point where tails next is not null, which is in between when we haven't finished moving these things around, when the tail's still pointed at the old final node. So that last line is going to make sure that the tail's now pointed at the current final node after we've just added something in. So this is the interesting thing about when I use a pointer, and I'm going to where the pointer is aiming at, or am I changing the pointer itself? So there's two different things going on here. This is the tail pointer. This is the next that's inside the object that the tail pointer was aimed at. So looking at how many of these things there are and what the last thing is in each of these is going to help you decide exactly where you are. So if the last thing in this is next, I'm looking at the next pointer that was inside the tail, that's inside the queue. That's the thing I was changing. Then here I'm looking at the tail pointer, which is inside the queue. That's the thing that I'm changing when I'm changing it to this. So first thing is I take whatever the final node was and its next aims at the new node. Then I take the pointer that was aimed at the final node and I point it at the new final node. So much going on in so little code, which is why I like to draw diagrams of these things, because the code itself does not have enough information in it for us to fully understand it without seeing some images. William, no such thing as a dumb question, totally okay to answer that. The main only includes the H file, yes. So how is it using the code from the other C file? Is it because we compiled them together? Answer your question is yes. When we compile multiple things together, so note that DCC mainfile.c q.c output to one program, qdemo. The fact that they go to one program means all of the C stuff is all compiled together into one big set of instructions. The H file is the thing that links these things together by name. So the only reason the main file can call those functions that exist in the other C file is because it knows their names. If it knows their names, it can ask for the code. If it doesn't know their names, it won't be able to use the code, even though the code is there in the same program. So the code's there in the same program. The H file says, okay, here's how you get access to the code. The cool thing about the H file is it doesn't tell you that the struct is there, so you don't know that the struct is there, even though it's actually in the same program. So that's how we protect the difference between things. But the H file says, let me tell you something, there's these names of these functions. Someone else is going to deal with those functions, make them exist, but since you know the names, you can find them. It's like summoning demons. That's a completely different thing, but you know. Okay. Alright, apologies, there was lots of confusion, but there's always lots of confusion. First time we see anything, it's going to be confusing no matter what. So don't worry about that, that's always going to be the case. With these abstract data types, we're going to use them more than we're going to fully understand them at this point. And I'm totally okay with that, because I feel like a lot of what we teach in COMP1511 is the first time you've seen stuff. First time you see something, I have no expectation of you being able to use it yet, you know. I'm happy for you to see something and go, that is whack. I don't know what's going on there. And then the second time you see it, you go, I remember that confused the hell out of me last time. Now I know a little bit more about it. And then you see it again in a couple of months or something like that in another course. You go, wait up, Mark was showing us those things. Now I see them in another context. I've learned all this other stuff about programming. I think I can get a handle on these. So if you're feeling that way about pointers, memory allocation and stuff like that, then yeah, I understand. I understand that there's going to be issues. If you're feeling that way, especially about these abstract data types, don't even worry about it, because we're so late in the course that with these abstract data types, I'm kind of going to introduce them to you, knowing full well that we don't have enough time in this course for me to cement these topics. Pointers, I want to hopefully get you to a point where you have a decent understanding of them. Memory allocation maybe less so, abstract data types even less so. So I'm happy for people to pass this course without a full knowledge of those things. But that's fine, because you'll pick it up again later as you see these things again, and then it'll be really funny because another lecturer will be like, have you learned this? And you'll be like, oh, I'm not really sure about it. And then when they start using it, you'll be like, oh, I can use this, and you'll actually have more knowledge than you think you have. So don't worry about it if not everything is sinking in at the beginning. Okay, other things. Is tail like a copy of the last item of the queue? Importantly, not a copy, but a reference to it. So if it's a pointer to the last item in the queue, it gives you access to the last item of the queue, but there's still only one last item of the queue. That's what Georgia was asking there. Sam, it's like summoning demons. All makes sense now. Yeah, if you know the demon's real name, then you have more control over it. Tyler is asking, I have a Word doc full of lecture notes and contains screenshots of your slides. I want to share my notes with students taking COMP1511 later in the year. Do you mind? Should I just reference you? Yeah, if you want to, you can. Especially like if you do stuff with CSE SOC and stuff like that, they do helpful things like that. I would be a bit yes and no about it. Not because I don't mind you using my stuff. My stuff's publicly available. But the more people use my old stuff instead of my new stuff, the less they get the revisions that I put in it. So I don't know whether I should or shouldn't say this, but like there are issues with the way that we taught stuff this term. I've already written down all the things that I thought I made mistakes in, and I'm going to change them for subsequent terms. And so the more that people look at one specific iteration of COMP1511, I apologize, right? Because this is like me saying you're getting taught worse than whoever's getting this in term 3, but it's the truth. And if it wasn't the truth, I would be a bad lecturer. So I'm supposed to be improving as I go on. And so the issue with us having a particular set of my notes and stuff from one particular term is that if I make changes or improve it and decide to teach things in a better way, then I don't necessarily want the old stuff sitting around, because it could confuse people, especially because if it did confuse people like it's confused you, then I usually want to change stuff to try to teach them a different way. I mean, I have no problem with you saying, look, these are some past notes, these are Mark's notes, these are what I wrote for how I understood it, and stuff, but I would also like to point people always at the most recent, because I think the most recent is going to be my best teaching. But we'll see how we go with that, So I don't have a problem with you doing it, and yes, I would definitely like to be credited if you're going to chop and change it, so there's bits that don't have my name in it and stuff like that. Yeah. Sam's asking, something like a queue, would that be an example of something we wouldn't generally write over and over again? We'd reuse that code generally. Yeah, totally. So, Sam, when we create a queue as a data structure, we would never want to create another queue, because if we've created one that follows the rules, we would never need another one. There are actually queues. I don't think the C standard library has it, but C++, which is like just a sort of, the funniest way to say it is a dirty hack built on top of C. That's what some people call C++. I'm actually a C++ native speaker, so my native speaking programming language is one of the messiest languages in existence, and it just so happens that's the one that I've done the most. C++ has a queue. So you never actually have to implement a queue when you're using that language. I think Java might have one as well. So a lot of the C-based languages have a thing where you just do #include queue.h, and then that's it. You never have to work with it. You just go, I'm going to put this type of struct inside this queue, and that's it. We're done. Oh, Tom, aren't you teaching now, Tom? Don't you have a... Oh, wait. It's Tuesday? No, do you normally... I don't know. Yeah. Yeah. The more you learn about C++, the weirder it gets. Which explains me. I've been shaped by the language I learned the most. Okay, let's go back to actual questions. Yeah, so Sam's saying we've reused the code. Tyler's saying... oh, right. You're doing biomed. Well, biomed still has, I think, potential for coding in it forever. So you never know, because it's all about, I think biomed's all about technology for medicine. So I think there may be coding in your future anyway, so you never know. Yeah, Tom. No, that's right, because you teach Monday and Wednesday, and today feels like Monday because it's the first day of the week. Even though I was working yesterday anyway, but I tried not to work too much on the public holidays. Okay, let's wrap it up there. We've gone way over time, but I feel like that's fine because people just wanted to stick around to get some questions answered. So we'll wrap it up where we are now, and I will see you all tomorrow. We will continue. Obviously, this code is not finished. It's got memory leaks all through it. There might be other issues with this we haven't found yet, so we're going to look at it more tomorrow. We're going to add some more capability to it, and also introduce the idea of stacks, which is another abstract data type. So I want to show you more than one to show you a couple of things. All right, see you all later.